Hello, here is Jaroslaw Stakun speaking. I'm Principal Solution Architect at Red Hat. In this presentation, I would like to give you an introduction to Red Hat microservices products. So first I would like to start with some quick recap of the microservice architecture. So basically the goal of microservices architecture is to decompose the application into set of services that runs independently and communicate each other. So this is also architecture that is very similar to what we know as a distributed architecture. So basically in the distributed architecture we have a set of the independent services and they communicate or could communicate each other via some APIs. So this architecture will introduce an additional complexity when it comes to the communication between the services, and in order to solve that complexity we have created a service mesh. So a service mesh is a dedicated infrastructure layer for handling service-to-service communication. It is responsible for reliable delivery of requests through the complex topology of services that comprise a modern cloud-native application. In practice, the service mesh is typically implemented as an array of lightweight network proxies that are deployed alongside application code without the application needing to know that it is part of the mesh. So the Red Hat Service Mesh is combined of number of components. So of course the heart of the system is based on the Istio project, which has been extended with some additional monitoring and observability solutions like Prometheus, Grafana, Jaeger, and the Kiali console. So the service mesh is part of the OpenShift container platform, and it allows you to deploy multiple meshes within single OpenShift container platform cluster, thanks to its multi-tenant functionality. So the main question when we talk about the microservices architecture is how are we going to deal with its complexity. But first let's see what does it really mean. So first of all, the microservice architecture introduces a complexity in the way how we deploy our services. Secondly, there is a challenge of deploying, implementing the communication and managing the communication between the microservices, which includes things like configuration management, service discovery, routing management, fault tolerance, tracing. So all the aspects of the network communication. And also we cannot forget that the microservices architecture is really technology independent. So it means that we might have different microservices developed using different technologies, so in the polyglot fashion, and also we might want to include into our service mesh existing applications that are not really microservices based, or they are not aware of the microservices architecture. So the solution for those challenges is really to prepare and deliver the infrastructure that will address those complexities. And this is basically how Service Mesh is created. So Service Mesh is a dedicated infrastructure layer for service-to-service communication. So when the microservices architecture was invented back in around 2014, those challenges related to the service-to-service communications were typically addressed by developing a dedicated libraries that were included into the microservices implementation, which of course made those microservices really kind of technology dependent, because those libraries, they were developed in some programming languages. So this was kind of creating a requirement to implement microservices using the same technologies. But over the time, those functionalities were moved outside of the services implementations to the underlying infrastructure as a service mesh. So the infrastructure, of course, is containerized and is based on the Kubernetes. So with the Kubernetes and containerization, we can also benefit from the automation of deployment the services into the infrastructure, so that we don't have to deal with the large amount of individual services, but we can leverage automation to deploy those services using this single infrastructure and the same process at a large scale. So the service mesh architecture consists of two layers. So we have a control plane layer where we have all the components that are managing our service mesh. So here we can use the tools that will allow us to implement the security, authentication, authorization, routing, and also the monitoring stack. And then we have a data plane. So the way it works is that you will install into every service pod, you will install additional sidecar container that will act as a local network proxy. So it is based on the Envoy, and this Envoy will intercept all the traffic that will reach the pod, and also it will maintain the traffic that is going out of the pod. So that this is a place where those policies that were implemented on the control plane will be executed. So service mesh provides a number of capabilities when it comes to the service-to-service communication management. So first of all, it will help you to manage the fault tolerance of your network. So it implements network patterns like circuit breaker. It allows you to implement timeouts and retries for the request. It also allows you to define some throttling limits, limiting the amount of requests that could hit your service. Then it also can take over all the network security capabilities. So it means you can implement at service mesh layer transport level security, including the mutual TLS, and also you can implement different access, so authorization and authentication policies. With service mesh, you can also benefit for the chaos engineering pattern. So here you can define some policies that will inject some faults, some errors into your application, so that you can test and verify how your application can deal with those situations. Then you have a possibility to implement some dynamic routing, so you can define some policies that allows you to implement scenarios like canary deployment, AB deployment, dark launches. With service mesh, you can also manage and monitor your services communication. So there is a distributed tracing included based on the Jaeger. There is also access logging implemented on every layer, so you can get detailed information about the access to your services, and it is also a fully multi-tenant, so that you can deploy multiple service meshes within one cluster. Last but not least, in Service Mesh there is a Kiali console, which allows you to implement comprehensive observability functionality, so that you can visualize your service mesh and you can trace the traffic that is executed in your mesh. So the service mesh, we can manage the communication between the microservices, and with Red Hat runtimes you can basically implement the logic of your microservices. So because microservices by design do not enforce you to use any specific framework or any specific programming languages, also in the runtimes we offer support for multiple different frameworks and languages depending on your needs, your experience and your requirements. So if you are a Java enterprise developer, you can deploy microservices on top of traditional J2E application servers like JBoss Enterprise Application Platform. If you are experienced Java developer and would like to implement more lightweight style services using the micro profile specification, you can leverage frameworks like Thorntail or OpenLiberty. Also, if you are Spring developer, you can use Spring. If you prefer Node.js and JavaScript, you can use Node.js here, and the others. So the one framework I would like specifically focus on here is the newest here, the newcomer here is the Quarkus framework. So the Quarkus framework has been built on top of existing Java, mostly Java enterprise frameworks and components like OpenJDK, of course, the Whitefly, the micro profile, and some implementations of this framework. So it really means that if you would like to start using Quarkus, you don't need to learn a new framework. You just will need to use different libraries as a dependencies to your existing Java EE or micro profile applications. So the main goal of Quarkus framework is really to optimize the resource consumption of Java running in containers. So Java by design is not really a good fit for containers, because Java by design does a lot of processing at the Java virtual machine startup time. So the features like reflection, class loading, these are examples of the JVM capabilities that are executed at the Java startup time, which is not a good fit for containers, because the idea of containers is that we can start very quickly a container and it is up and running in very short time. So in Quarkus, those capabilities that are very beneficial in a traditional Java environment has been moved into the compilation time. So the Quarkus compiler does a lot of optimization at the compilation time, so that when you have a program running, the compiled program running, it will start very fast and it will consume much fewer memory than the traditional Java application. So with Quarkus, you can build a program using the traditional JVM. So, for example, the hotspot JVM, or you can even move further and use the GraalVM compiler to compile your application into the native executable, which then could be packaged into the container and will start super fast, so it can start in really milliseconds and will consume much fewer memory than traditional JVM. So what are the differentiators and the benefits of using Quarkus? So as I said, it is a container first technology, so the Quarkus has been built, created in order to let you run Java based applications in a containers in the most efficient way. It also provides some utilities for developers, like live coding, for example, which allows you to really very quickly redeploy changes that you are doing in the code, so that you can see very fast working the changes you have implemented in the code. It also supports different programming paradigms, so both the imperative and reactive. So depending on your skills and your experience, you can pick the best for you frameworks. And there is a big effort in the Quarkus community to kind of Quarkify as many as possible different existing libraries and standards and frameworks. So I mentioned microprofile, J2E, also there is a integration with the Spring framework, with the Vertex. Also for the integration logic, we have integration with we have frameworks for Apache Camel. So there is a very comprehensive and even growing set of libraries that were Quarkified and they were made supported in the Quarkus environment. So I do encourage you to try Quarkus if you are a Java developer, if you are developing microservices using Spring or microprofile. This is a very good fit to run those applications in containerized. So this concludes my presentation about the Red Hat microservices stack. So I discuss basically two major components, so the service mesh for implementing microservice communication in the distributed architecture, and the Red Hat runtimes, including the Quarkus frameworks, which are a set of frameworks that you can leverage to develop new microservices in a cloud native fashion. Thank you very much for your attention, and bye.